Hello, welcome to this video. I'm going to be talking about recurrent neural networks. Now let's start off with a phrase, right? This is amazing. And Yoda would say the same phrase as amazing this is. Now, amazing is shared, right? And so is this is. But let's focus on the word amazing. So we have a neural network, right? But there's two different positions for the word amazing, okay? Each word is processed separately. And as a result, there's two different sets of weights for the same word, amazing. So two sets of predictions using the same word, this is not the problem. The problem is the different set of weights. So the problem is clear. FFNs learn the same word multiple times, once for every position it appears. What if instead of separate weights for each position, we use the same weights at every time step and added a memory that passes information forward? The recurrent neural network would have the same weights for the same word amazing. This would eliminate the redundancy. Now we have this recurrent neural network here. And basically we could see that the weights are being carried forward, right? So RNNs use the same weights, W1, W2, and W3 at every time step. This weight sharing combined with the hidden state, H, that passes information forward is what gives RNNs memory, right? So now we're going to try applying the activation and softmax function. We have W1 is Wx to H, so that's the input to the hidden layer. We've got H to H, which we see in that self-referencing circle. And then we have WH to Y, which is the hidden layer to the output layer. So this is the activation function in the HT. We've got tan H, WXH, XT, plus WHH, HT minus 1, plus BH, which is the bias layer. Then we've got the softmax, right? It's WHY, HT plus BY, right? Because we're going from the hidden to the output. Then backpropagation, basically the weights adjust through time. So we have the loss W1, loss W2, loss W3. And you could see this backpropagation through time, okay? Notice that the losses for all the weights are similar, right? But we're using it at each time step, xt minus 1, x, and xt plus 1. And here's the loss of negative log of yt, which we're trying to minimize. And this generalizes to xt minus 1 and xt plus 1. So gradient descent also updates weights until loss is minimized for all time steps. Okay. And you could, again, like I'm going to reiterate, it could generalize to xt minus 1 and xt plus 1. So the total loss of the sum of negative log yt is minimized. So RNN does have some problems. Let's discuss the vanishing gradient problem. So RNN struggles to remember long-range dependencies. Backpropagating through time requires more multiplications of the hidden layers. So just to illustrate, like the more you multiply something, especially if they're in decimal places, they're going to get smaller and smaller and smaller. So let's see this. So in RNNs, t equals the number of time steps, the number of words in the sentences. Okay, so that's equal to the number of the words in the sentences. And we could see this basically, the loss with respect to h1, right? And we're going back t minus 1, t minus 2, and so forth. Now we have t equals 50, 0.9, t equals 49, 0.81. So we're multiplying by 0.9 downwards, 0.73, 0.66, and so forth and so forth, and it gets to 0.006. So how the current hidden state changes with respect to the last hidden state, the gradient with respect to h1 accumulates contributions from all future hidden states because h1 influences h2, which influences h3, and so on, all the way to the final loss. So vanishing gradient happens because the RNN updates its memory by repeatedly multiplying the same number at each time step. If the number is less than 1, which is almost always is, the signal gets smaller and smaller as you go backward through a long sentence. After many steps, the gradient becomes effectively 0, so the network can no longer learn from words that appeared early. That's why simple RNNs forget the beginning of long sentences. Thanks for watching, and I hope to see you soon.